Today we are going to learn about vectors and scalars, unit 1.3. So let's see our learning objectives today. So we will learn to distinguish between vectors and scalar quantities and resolve a vector into its components, reconstruct a vector from its components, and carry out operations with vectors. So now let's read. Quantities in physics are either scalars, that is, they just have magnitude, or vectors, they have magnitude and direction. So the main thing we have to focus on is that scalars, they just have magnitude and they don't have direction, whereas vectors, they have magnitude and direction both. So this section provides the tools you need for dealing with the vectors. So now, vectors. Some quantities in physics, such as time, distance, mass, speed, and temperature, just need one number to specify them. These are called scalar quantities. For example, it is sufficient to say that the mass of the body is 64 kilograms, or that the temperature is minus 5.0 degrees Celsius. On the other hand, many quantities are fully specified only if, in addition to a number, a direction is needed. So, like, we have some quantities here: time, distance, mass, and speed, and temperature. So, we just need a number, like any number, to specify them. These are the scalar quantities. So, now let's read. Saying that you will leave Paris now in a train moving at 220 km per hour. Do not tell us where you will be in 30 minutes, because we do not know the direction in which you will travel. Yes, do not we don't know the direction in which the person is traveling. We just know the time. So quantities that need a direction in addition to the magnitude are called vector quantities. Like, quantities that need a direction in addition to magnitude are vector quantities. So vector quantities have magnitude as well as direction. So we have some examples here in the table. Let's see. So vectors. Displacement is a vector quantity. Distance is scalar quantity. Vectors, because displacement, it has both magnitude as well as direction, and distance, it has only magnitude and not a direction. So now velocity the same. Here we have direction and magnitude, but in speed we just have magnitude. So acceleration is also vector quantity, and mass is a scalar quantity, and force is vector quantity, and time is scalar quantity. And force has magnitude as well as direction, because force is always applied in any direction, right? But time has no direction, and it only has magnitude, like 30 minutes or 20 seconds. So weight weight is also a vector, because it has magnitude and direction. And density is a scalar quantity, it only has magnitude. Electric field has magnitude and direction both, but scalars, like the electric potential. I think many of you, what is electric potential? So electric potential is a scalar quantity, it just has magnitude and no direction. And magnetic field, it is also a vector quantity, and electric charge is also scalar quantity. Gravitational field is a vector quantity, and gravitational potential, remember, gravitational field and gravitational potential. The potential is the scalar quantity, whereas vector quantity is gravitational field. And momentum momentum is a vector quantity, and temperature is scalar quantity. Area is vector quantity, and volume is scalar quantity. Angular velocity is vector quantity, whereas work, energy, and power are scalar quantities. They just have magnitude and no direction. Whereas angular velocity, like the velocity we have here, just like that, angular velocity is also vector, because it has magnitude and direction both. So the simple way is, like, vector quantities have both magnitude and direction, but scalar quantities just have magnitude. So let's go on. A vector is represented by a straight arrow as shown in figure 1.10. The direction of the arrow represents the direction of the vector, and the length of the arrow represents the magnitude of the vector. To say that two vectors are same, it means that both magnitude and direction are the same. The vectors in the figure 1.10b are equal to each other. In the other words, vectors do not have to start from same point to be equal. So like here, the direction of arrow, like the direction of arrow of the vector, and this length of the arrow represents the magnitude. This length represents the magnitude, and this direction, this resembles the direction. And the vectors in 1.10b are equal to each other. Yes, the magnitude is equal to each other, and direction is also equal. So we write vectors as italic boldface a, like this variable a, and the magnitude is written as like these in between the bars. This is the mod a, or just we can say a. Representation of vectors by arrows is this one, and three vectors are equal to each other. Their direction is also equal and magnitude is also equal. Now here comes multiplication of a vector by a scalar. A vector can be multiplied by a number. Yes, a vector can be multiplied by any number. The vector a multiplied by the number 2 gives a vector in the same direction as a, but 2 times longer. Hmm. The vector a multiplied by minus 0.5 is opposite to a in direction and half as long, like in figure 1.11. The vector minus a has same magnitude as a but is opposite in direction. So figure 1.1, it shows like this. So multiplication of vectors by a scalar, if we multiply them. So yes. Now addition of vectors. Figure 1.12a shows vector d and e. Okay, we have d and e. We want to find the vectors that equal d plus e. Okay, we have to like add both the vectors. So if we add up these vectors and like join these, and we know we get a magnitude like in between them, like this represents the magnitude. This is like the method of adding them, and it can also be like this, like let's read it here. Vectors d and e. Adding two vectors involves shifting one of them parallel to itself as to form a parallelogram. We like see this is a parallelogram, like same sides. Okay, so with two vectors as the two sides, the diagonal, this is the diagonal, represents the sum. And in figure C, we can see an equivalent way to add vectors. Now, to add two vectors, we have the 3 points here. Draw them so they start a common point O. Complete the parallelogram whose sides are D and E, just like we have here. And draw the diagonal of the parallelogram starting at O. This is the vector D plus E. And now, equivalently, you can draw the vector E so that, like here, where the vector D stops and then joins the beginning of D to the end of E as shown. This is just the way they are like to show this is the equivalent way to illustrate this figure. Now let's see this exam tip for us. Now these are the three vectors given up, like they are denoting different directions, and it forms a triangle, right? And this forms another shape, I don't know. So figure 1.13, this is the vectors with arrows pointing in the same sense forming closed polygons, like they are forming closed polygons. This is also polygon, this is also polygon, but we know this is a triangle. So add up to 0. Okay, now subtraction of vectors. So figure 1.14 shows vectors d and e. We have here vectors d and e. the magnitude is this, and the arrow is representing the direction. Okay, so we want to find the vectors that equals d minus e. So like taking out the difference between them, to subtract the two vectors we have the 2 points here. Let's read them, draw them so they start a common point O. Like this we have to draw like this. Okay, look at this carefully. Now the vectors from the tip of the E to the tip of D is the vector d minus e. Notice that is equivalent to adding d to minus e, like this. These all vectors denoting in the different direction, and these two vectors are like in the opposite direction. It is like here and it is upward, so this e and minus e, and this is the equivalent way of just taking out the difference of d and e. You can look here, and oh, we have exam tip here. This the change in the quantity, and in particular the change in the vector quantity, will follow us through this entire course. You need to learn this well. Okay, we have an example here, 1.14. Copy the diagram in figure 1.15a. Use the diagram to draw the third force that will keep the point P in the equilibrium. Okay, to keep the point P in the equilibrium. So A part and the B part. Okay, this vector is denoting in the downward direction. This is denoting in the direction somewhat here. Let's see. So we find the sum of the two given forces using parallelogram rule, right? And then draw the opposite of that vector as shown in figure 1.15b. Let's see that. Oh, 1.15 is like this. This is 1.15b. We have to do like this. So the sum of the two given forces, like this is the parallelogram rule, and we draw the opposite vectors. Like if we draw like this, and this vector is opposite to this, so we can make a parallelogram out of it. So this is the parallelogram rule. So now 1.15 example, a velocity vector of magnitude 1.2 meter per second is horizontal. Second velocity vector of magnitude 2.0 meter per second must be added to the first so that the sum is vertical in direction. Find the direction of the second vector and the magnitude of the sum of the two vectors. We need to, like here, we need to draw a scale diagram, okay, as shown in figure 1.16 down here, using a scale diagram to solve the vector problem. So representing 1.0 meter per second by 2 centimeters, we see that the 1.2 meter per second corresponds to 2.4 centimeter, and 2.0 meter per second to 4 centimeters. First draw the horizontal vector, then mark the vertical direction from O using a compass or a ruler. We can use compass. If anyone doesn't have the compass, you can use a ruler. Okay, mark a distance of 4.0 centimeter from A. Okay, and then which intersects the vertical line at B. So AB must be one of the sides of the parallelogram we are looking for. Now measure a distance of 2.4 centimeter horizontally from B to C, and then join O to C. This is the direction in which the second velocity vector must be pointing. So measuring the diagonal OB, that is the vector representing the sum, we find 3.2 centimeters, which represents 1.6 meter per second. Measuring the diagonal OB, this is the diagonal. So using the protector, we find that 2.2 meter per second velocity vector makes an angle of about 37 degrees with the vertical. Okay, velocity vectors, it makes an angle of 37, like in between the two vectors. Okay, so now let's move on to another example. So here we have 1.16. A person walks 5 kilometers east, followed by 3 kilometers north, and then another 4.4 kilometers east. Find their final position. So the walk consists of three steps. Okay, we may represent each one by vectors, just like in figure. The first step is a vector of magnitude 5.0 kilometer directed east, like the OA. OA is here, the 5 kilometer towards east. And then the second is a vector of magnitude 3 kilometers directed north, like the AB. And the last step is like represented by a vector of 4 kilometers directed east, like the BC. It's also in the east direction. So vectors corresponding to line segments shown as the bold capital letters, for example OA, the magnitude of the word that vector is the length OA and the direction is from O to A, like the OA. Okay, direction is from O to A, yes, we know. The person will end up at the place that is given by a vector sum of these three vectors, that is OA plus AB plus BC, which equals the vector OC. By measurement from a scale drawing or by simple geometry, the distance from O to C is 9.5 kilometers, 9.5 kilometers, and the angle to the horizontal is 18.4. Okay, angle to the horizontal is 18.4. And now, okay, hope you understand this example. And now the next example we have here, 1.17, a body moves in a circle of radius 3.0 meter with a constant speed of 6 meter per second. The velocity vector is at all times tangent to the circle. The body starts at A and proceeds to B and then to C. Find the change in the velocity vector between A and B and between B and C. So let's look at the figure 1.18. We have a like this circular path here. This is the vector, like, or like it's like moving like this, so the direction of force will be like here. Okay, and it's like moving, so the force applied would be like in this direction, and the force, it's like if it's like in circular, so then the force would be like here. If the point would be like here, then direction of force would be like here. Okay, so yes, let's see the solution. uh, for the velocity change from A to B, we have to find the difference VB minus VA, VB minus VA. And for the velocity change from B to C, we need to find VC minus VB, okay, for velocity change from B to C. And this is from velocity change from A to B, okay. The vectors are shown in figure 1.19. This, let's see this figure. These are the two vectors, it's their difference denoted here, VB, and VC minus VB, and this is VA minus VB, or like the VB minus VA. So now the vector VB minus VA is directed southwest, and its magnitude is given by the Pythagoras theorem, like hypotenuse and the perpendicular and the base, like VA square plus VB square equals 6 raised to power 2, and 6 raised to power 2 is a 6 square, and it's 72, how, like 6 are 36 and 36 twos are 72, so its root is 8.49, and the vectors VC minus VB has same magnitude as V minus VA, but the direction is northwest. V minus VA, but the direction is northwest. V minus, yes, it's northwest. So look at here, if you can see the figure, yes. Okay, so let's move on. So the component of a vector, suppose that we use perpendicular axis x and y and draw vectors on the xy plane. We take the origin of the axis as a starting point of the vector, like we take the origin is like this. Oh, okay. Other vectors whose beginning points are not at the origin can be shifted parallel to themselves and until they too begin in at the origin. Given a vector A, we define its component along the axes. Okay, this is the vector A, and this x-axis and this y-axis, like the y component here, and this is the x component. So from the tip of the vector, draw lines parallel to the axis and mark the point on each axis where the line intersect the axes. Figure 1.20. Mark the lines. And now let's move on. The components of the vector A and the angle needed to calculate the components. The angle theta is measured counterclockwise, like the counterclockwise from the positive x-axis. Okay. And then now the x and the y components of A are ax and ay. Like the ax, if it's like the y component, then it is a y and ax. Okay, so ax is a cos theta and ay is a sin theta. Ax is a cos theta and ay is a sin theta, remember this. And where a is the magnitude of the vector and theta is the angle between the vectors. Okay, theta is the angle between the vectors. So vector and the positive axis, these formulas and the angle theta defined as shown in the figure 1.20 always give the correct components with the correct signs, but the angle theta is not always the most convenient. A more convenient angle to work with is this, the simple phi, like the note here is phi. But when using the angle, the signs have to be put in by hand. This is shown in worked example 1.1 and we will see that. So now here we have an exam tip. So formulas given for the complement vectors can always be used, but the angle must be one defined in 1.20. Yes, it should be defined, and which is sometimes awkward. Yes, you can use other more convenient angles, but the formula for the components may change. It can. Okay, now let's see the worked example. We have 1.18. The find the components of the vectors in figure 1.12. The magnitude of A is 12 units and that of B is 24 units. So like here, A is 12 units and B is 24 units, and we have angle here 45 degrees and 30 degrees. This is a y component and this is x. So now taking the angle from the positive x axis, the angle for A is theta equals 180 degrees less 45 degrees equal to 225 degrees. Like we have to add it. You know it, like, yeah, and that for the B is theta equals 270 plus 60 gives 330. Look at here, this is whole 180 degrees, so we can easily find the angle, right? And then ax component ax component is 12, like here is 12.0, like the 12 cos theta. Theta is our here 225 degrees, and ax is minus 8.4. Then if we calculate it, and then bx is equal to 24 cos 330. It's like here, so bx equals 20.8, and ay is the y component. Ay is the 12 sine 225, and then the value we get is negative of 8.49, and by is 24.0 sine 330 by, then we get negative of 12.0. But we do not have to use these awkward angles of 225 and 330. For vector A, it is better to use angles of like 5 or equals 45, and that case simple trigonometry gives like ax equals minus 12.0 cos 45 degree equals minus 8.49, and ay component here is like negative of 12 sine 45, which is minus 8.49. Now for vector b, it is convenient to use angles phi equals 30, and which is the angle that the vector makes with the x-axis, but in this case bx equals 24 cos 30 20.8, and the y component by gives negative of 24 sine 30, which gives negative of 12. Now let's move on. So find the components of the vector W along the axis shown. So now this is our, like, the shape, the triangle. We have angle theta here. These are the marked lines, and this is the direction of the weight, like the vector V, I think, vector W, sorry. And now let's see the solution. So figure 1.23 here. Notice that the angle between the vectors W and negative y-axis is theta. Then by simple trigonometry, Wx gives negative of W sine theta and Wy gives negative W cos theta. Like here, Wx is opposite to the angle theta, so the sign is used, but Wy is adjacent to the angle theta. Look here, it's adjacent to angle theta, so the cosine is used. Like, look at the figure here carefully. This is the y-axis and this is x-axis. This is angle theta. This is the x component of the vector W, and this is the y component. This is the W vector. So both components are along the negative axis. So a minus sign has been put in by hand, like the negative, like the downward. Like this is the positive part, and this is also, this is like the, and this is the positive, because like here both the x and y components are positive, and this is, and here the y component is positive but the x component is negative. And like in this part, the x component is also negative and y component is also negative, and here also the x component is negative and y component is negative, so we can take it both negative. So that's why. So reconstructing a vector from its component, knowing the components of the vector allows to reconstruct it, that is to find the magnitude and the direction of the vector. Suppose that we are given that the x and y components of the vector are fx and fy. We need to find the magnitude of the vector f and the angle theta it makes with the x-axis. The magnitude is found by using the Pythagorean theorem, and the angle by using the definition of tangent. So knowing the component vector allows it to reconstruct. Yes, the magnitude and direction. Remember, vectors have magnitude and direction. If you have to remember this, and so like we have to think, like suppose that we are given x and y components of the vector, like fx and fy, then we need to find the magnitude of vector f and angle theta it makes with the x-axis. So the magnitude is found by using the Pythagorean theorem, and the angle by using definition of tangent. So f gives root over fx whole square and plus fy whole square, then theta equals arctan fy over fx. So as an example, consider the vector whose component are fx equals 4 and fy equals 3, and the magnitude of f is f equals root fx square plus fy square gives 4 square plus 3 square, and which gives root over 25, which is 5. Like you can look at this figure, like this is the f component on the y-axis fy, and this on the x-axis like the fx, and here we have theta. So f, this is the f vector, maybe the f force. Okay, so here, and the direction is found from theta equals arctan fy over fx, and arctan 3 over 4 gives 36.87, which is approximately 37 degrees. So fx is like here and fy is here, so, and the component, then the vector will be like here, the direction and magnitude. It's in the third quadrant. So here is another example. We need to find the magnitude and direction of the vector in the component fx equals -2 and fy equals -4. The vector lies in the third quadrant as shown in figure 1.25 is here, and f equals root over f x square plus fy square equals root over minus 2 square plus minus 4 square, then which gives us this value approximately 4.5. The direction is found from phi. Remember this phi equals arctan fy over fx, and which also equals arctan minus like the negative 4 over negative 2, and it equals arctan 2. Then the calculator gives theta equals tan inverse 2 equals 63 degrees. This angle is the one shown in figure 1.25. The general and the simplest procedure to find the angle without getting stuck in trigonometry is to evaluate phi equals arctan fy over fx like this in mod. So ignore the signs in the components. So calculate the calculator will then give you the angle between the vectors and the x-axis as shown in figure 1.26. So adding and subtracting vectors is very easy when we have the components as worked example. Like here, you can look here, this is the angle phi and this is the vector going up here in this direction, and these are the y-axis and these are the x-axis. So these, look at here, the angle phi is given by phi equals arctan fy over fx. So remember this formula. Now we have worked example. Find the sum of the vectors shown in figure 1.27. F1 gives like f1 has magnitude 8 units and f2 has magnitude of 12 units. Their direction are as follows in the diagram. So like the y component and the the y-axis and the x-axis, like this one vector f1 here and f2 another vector, then their magnitude, like adding them, is f1 plus f2. You can imagine this a parallelogram, and this angle is 42 degrees and this is 28 degrees. So now we have to find the sum of the vectors. Okay, so find the component of two vectors like here, f1x, which gives a negative f1 cos 42, f1x gives minus 5.945, and f1y gives f1 sine 42, f1y equals 5.353, f2x gives f2 cos 28 degrees and f2x is 10.59, and f2y is f2 sine 28, and f2y then we get is 5.634. Then some of the vectors that we have to find is fx is like f1 plus f2, so we have 4.65 here, adding them, and fy, the y component, the f1y plus the f2y gives 10.98. The magnitude of the sum is therefore f gives root over 4.65 whole square, and adding 10.987 whole square, which gives f equals 11.9 approximately 12, and its direction is phi equals arctan 10.987 over 4.65. Phi equals 67.1, which is approximately 67. So we have nature of science now. Let's read it. For thousands of years, people across the world have used maps to navigate from one place to another, making use of the ideas of distance and direction to show the relative position of the places. Like many thousands of years ago, people across the world have used maps. Of course, many, like today also we use maps, but not the like the paper chart maps. We use the Google Maps. And the concept of vectors and the algebra used to manipulate them were introduced in the first half of the 19th century to represent real and complex numbers. Okay, the first half of 19th century seems interesting. In a geometrical way, mathematicians developed the model and realized that there were two distinct parts of their directed lines, scalar and vectors. Scientists and mathematicians saw that this model could be applied to the theoretical physics, and by the middle of 19th century, vectors were being used to model problems in electricity and magnetism. Oh, that's cool. Resolving vectors into components and reconstructing the vectors from its component are useful mathematical techniques. Yes, like resolving the vectors into components. Vectors. Remember vectors. You remember what are vectors? Vectors are the quantities that have both magnitude and direction, and scalar quantities just have magnitude and no direction. Okay, and now these mathematical techniques are invaluable when dealing with the physical quantities that have both magnitude and direction, such as calculating the effect of multiple forces on an object. In this section, you have done this 2 dimensions, but vector algebra can be applied to 3 dimensions, and the more of it that we will learn in future. So that's all for today. And one thing, you can give me some example of vector quantities and scalar quantities in the comment box if you want. And that's all for today. And bye bye. Have a nice day.